The videos after the accident and after the explosion show containment leak as well. You'll see in the weeks afterwards steam coming from the center of the building. And I believe that the containment lid lifted on Unit 3 and never went back down straight. So it's lifted and twisted sideways, and radioactive gases are lifting from that containment lid. But there's not enough evidence to say that that's what caused the explosion that we saw during the accident. The jury's still out and will be for 10 years until we get inside the Fukushima reactor to see what the damage is. But right now, I think my theory accounts for the damage, the speed of the shock wave, and also the fact that the contamination has been found as far away as 2 kilometers.
Arnie, let's talk about the Unit 4 spent fuel pool. There's been a lot of questions about that and a lot of concerns right now. Was there a hydrogen explosion at the Unit 4 spent fuel pool? And if there was, what is a hydrogen explosion and why would it have occurred there?
One of the biggest mysteries of Fukushima is how did Fukushima Unit 4 explode? There's a couple of very, very grainy videos that clearly show it did explode. It was a different type of explosion and perhaps a fire and an explosion that went on for a period of days. So exactly how it did explode is one of the big questions about the Fukushima accident. There's 3 competing theories. Tokyo Electric says that the radioactive gases over in Unit 3 went through a pipe that connected Unit 4 and entered Unit 4, causing Unit 4 to explode. So Tokyo Electric's position is that the radioactive hydrogen that was created in Unit 3 went through a pipe, entered Unit 4, and there it exploded. Well, there's one piece of evidence that supports that. There's some contamination in some filters in Unit 4 that would indicate that gases did come from Unit 3. So that's a possibility. But I don't think it's accurate, because I believe that the containment was so damaged on Unit 3 that there was no pressure to push those gases into Unit 4. I can't understand how the gases, what the motive force was to push those gases into Unit 4. So I think the hydrogen explosion came from something inside Unit 4 itself. There's 2 possibilities there. One is by Dr. Kansai, and it's an excellent analysis. He believes that the hydrogen in the water in the pool that was dissolved because of the radiation in the pool over months and months and months was enough to cause the building to explode. As the water got hot in the fuel pool, it liberated the hydrogen that was in the water, and that hydrogen was enough to cause the explosion. The second possibility, and this is my theory, early on in the accident, there's some video that's up on our site that shows that the top of the fuel racks were exposed to air. Now, I'm not suggesting that the entire fuel pool ran dry, but the top of the nuclear fuel, I believe, was exposed to air, and I think the photos show that. So if the top of the fuel was exposed to air, it's possible that a reaction could have occurred at the top of the fuel that would have created enough hydrogen to blow the building up. So Dr. Saji and I agree that the hydrogen came from the Unit 4 fuel pool. He believes it was dissolved in the water. I believe it came from the fuel. And only time will tell when we get in to analyze the reaction. But there's an important lesson here that the nuclear industry is not taking into account, and that's the fuel pool temperature. The fuel pool is a large pool, and it can boil locally. And that's something the Nuclear Regulatory Commission and the international community is not looking at. You can get local boiling in a pool, even though the bulk temperature of the pool may be at 80 degrees Celsius. In portions of the pool, it can be boiling. Now, that supports Dr. Saji's comment that as it boiled, it would liberate hydrogen, even though the bulk temperature never ever exceeded boiling. Now, my theory is I do believe that the entire pool had drained to the point where there was boiling occurring. But the real issue here is that the nuclear industry is not looking at the fact that localized boiling can occur even though the bulk temperature might be less than 100 degrees centigrade. That's an important distinction moving forward. We have about 23 of these Mark I reactors in the United States, and there's another 10 or so around the world. And I think that we need to design these pools so that the hydrogen generated by dissociation can be accommodated without exploding the building. No one ever designed for that because no one ever anticipated it happening. But it did happen at Unit 4, and we need to prevent that in the future. Not just on these Mark I reactors, but on the 400 reactors that all have fuel pools that are all susceptible to that identical type of failure.
Arnie, I want to follow up with a few more questions. In your discussion of Unit 4, you've talked about its hydrogen explosion. Is there any chance of a prompt criticality or a hydrogen explosion now at Unit 4? Would anything cause it to release more fuel or more radioactivity?
The fuel in the fuel pool at Unit 4 has now been cooled for about a year after the accident, and it had been removed a couple of months before that. So the fuel is becoming cooler. It still needs to be water cooled for another 2 years, but it is much cooler than it was at the beginning of the accident. So the chances of hydrogen generation are much, much lower now than they were when the accident occurred. So I don't believe that we're going to see an explosion in the pool now, no matter what happens. My biggest concern is that if the pool loses water, then it's an entirely different story. So if there's a large seismic event that causes the building to topple or the pool to crack and the water to drain out, there's not enough cooling in the air of that fuel, and it will start to burn. Now, the consequences of that are, depending on which way the wind's blowing, it could mean the evacuation of Tokyo as a worst case. It could also mean cutting Japan in half so that the northern part is separated from the southern part by a band of contamination. So this is a very serious accident waiting to happen, and we just all have to pray that an earthquake doesn't happen before that fuel is removed.
Now, Arnie, compared to the accident at 3 Mile Island and Chernobyl, how dangerous are the radioactive releases from the 4 reactors at Fukushima Daiichi?
3 Mile Island was a level 5 accident, and Chernobyl and Fukushima are level 7 accidents. That means roughly that 3 Mile Island was 100 times less than the accident at Chernobyl and the accident at Fukushima. People did die as a result of the accident at 3 Mile Island. The Nuclear Regulatory Commission says no one died on their webpage, but the evidence is clear that there was an increase in cancer. I refer you to Dr. Steve Wing's report that's also on our site that talks about it. And in addition, some reports coming out of the University of Pittsburgh indicate just now that we're beginning to see leukemia as a result. So while 3 Mile Island was much less than either Chernobyl or Fukushima, people did die as a result of the radiation released. Now, at Fukushima Daiichi, the evidence tells us that at least 3 times more radiation in the form of noble gases were released from the units 1, 2, and 3 than from Chernobyl. We've seen radioactive gas clouds, noble gas clouds, to the northwest that are much worse than we ever anticipated to have been released. So we know that the noble gases were larger than Chernobyl. Now iodine, which is another gas that's released, and also cesium and other gases, seem to be roughly on the same level as the releases from Chernobyl. Now, there are two issues here. As terrible as it is, it would have been much worse but for two things. The first is that most of the time the wind was blowing out to sea. And of course, Chernobyl was surrounded by land. So whatever way the plume meandered after Chernobyl, it contaminated the land. So when we can compare Fukushima to Chernobyl, the total releases from Fukushima are likely higher than they were at Chernobyl. But because most of it blew out to sea, that's a good thing for the Japanese people. The second important thing that happened that was lucky, if we can call it luck in such a severe accident, was that it happened on a Friday and not a weekend. There were 1,000 people at the Danai site and at the Daiichi site because it was a weekday who could respond to the accident. If it had happened on a weekend, there would have been a small crew of people there, and the accidents at both sites would have been much, much worse. Now, that has an implication worldwide because on weekends and in the evenings, we have very small crews at these nuclear reactors. And should there be a major accident, there's no way to respond quickly enough with the small crew of people that are working on the shifts other than the main shift in the middle of the day. The international community needs to look at that. And it's not a matter of, well, we can get people there in half a day. That's too late. The staff on site has to be larger at the beginning of the accident to mitigate the potential for a serious accident. But yet it all boils down to money. The utilities that run these power plants really don't want a large staff because they have to pay for it. But in fact, it was the large staff at Daiichi and the large staff at Danai that likely saved the world. So the important takeaway here is that the releases from Fukushima are as serious, if not more so, than Chernobyl, and that they would have been much worse if the accident had happened on a weekend.
Arnie, thank you. How significant is the danger of hot particles, and why?
I'm really concerned about the hot particles that were released after the Fukushima accident. Now, a hot particle is more than just a single atom. An atom of cesium decays once and it's over. It's no longer radioactive. A hot particle, though, contains thousands or hundreds of thousands of atoms of cesium or other radioactive material. And they, of course, decay for many, many years and decades. So if a hot particle is lodged inside you, either in your lung or in your liver or in your gastrointestinal tract, it can cause a constant bombardment of radiation over a long period of time to a very small localized part of your tissue. And that's exactly the conditions that can cause a cancer. So we've seen in Mr. Kaltofen's analysis to the American Public Health Association, he shows what an air filter looked like in a car in Fukushima and what an air filter looked like in a car in Tokyo. Well, those air filters are no different than our lung. Our lung acts as an air filter. And that causes that radiation to get trapped in our lungs or in our livers or elsewhere in our bodies and will constantly, over decades, cause cellular damage. It's particularly a concern in young children because they have a longer life and because their cells are rapidly developing. So it's important that we monitor the children in Fukushima and throughout Japan over